Spectrum measurements. These are specific instruments tuned to very specific frequencies inside an energy region, right? So light has a spectrum, the rainbow, the colors of the rainbow. Electrical energy, AC electrical energy has a spectrum. It can be a DC voltage, right? 0 to however many DC volts you can make, or it can be an AC voltage or square wave, different types, different forms of wave shapes inside of electrical waveforms. Now remember, this is a pulse of electrons flowing through a wire we're measuring for electrical spectrum. Optical spectrum, we're looking at what the eye sees. We don't have a good way of measuring electrical spectrum ourselves other than when you get shocked. So we can recognize a high potential, but the low current stuff, not so much externally. Yet it's what drives us internally, all those little electrical impulses traveling up through your system. So optical emissions are photons, photon emissions from whatever elements are excited and emitting photons. And we can measure the wavelength, the color, the frequency of those photons and derive some information from them. That's optical emission spectroscopy. So back to the oscilloscope conversation, the electrical waves. I didn't start the oscilloscope conversation. Electrical waves traveling through a wire can have a frequency. Most have a frequency of some sort. So one of the first ways we started seeing these frequencies are oscilloscopes. They started out, probably one of the reasons TV sets were invented is those cathode ray tubes and what we can see on them. And today we've got color. Before we had off or green, or off or yellow, depending on the fluorescence on the surface of the tube. Those were sloppy days. We've gotten just better. That's how it is. I'm talking 200-year-old sciences leading into this. So that oscilloscope that's looking for a specific frequency, but it has limits. The frequency of AC current can be 0, then it's a DC voltage, or 60 hertz, that's what's out of your line, or out of your radio, it's in megahertz. Some things are in terahertz, and you can go beyond that in the frequency spectrum. But now we're looking at electrons and how we look at these things. Another video mentioned in the measurement sciences, there's two things done for an instrument. It's qualified and quantified. This is the heart of making that instrument, so you know what it does. Now what you see on the store shelf is related to that somehow, but the base instrument, that oscilloscope sitting in a lab, is specifically certified to do a limited range of measurements. So what am I talking? When you get into microwave frequencies ride on the surface of materials. They still need the good conductivity, but they ride on the surface of materials. So a radar set pumps those gigawatt pulses out through a square tube with a gold layer on each side of that square, facing each other, and that wave travels down that waveguide. The height of that waveguide is a specific dimension. If you bend the waveguide, you've done some not good for the radar set. So very well tuned, fairly precise instruments. You temperature control these things to keep the stability of the metals in the environment stable. That's how critical they are. So friend, acquaintance, associate, got laid off. His job for decades was with one of the oldest oscilloscope manufacturers actually on this planet, here hidden in the bowels of Oregon forests. And his job was building specific probes and oscilloscopes for high frequency measurements. This was a career. It still is. It's still being done. Just not as much because we've gotten better at it. So he gets laid off. Not a big deal, just a deal, another part of life. So these measurements are very precise, very tuned to specific things. On an oscilloscope, if you've looked at one, there's kind of two kinds of signals. There's a sine wave and a square wave. You get into peak envelope powers in square waves you don't particularly speak of in a sine wave. So a radar set blasts a pulse of energy out, and that pulse is a super high frequency pulse. So it can be interrogated besides the leading and trailing edges. But in an oscilloscope, if you look at a DC pulse or a high frequency pulse with the right equipment, one of the things you have to see is the leading edge of the pulse. And if your probe is not very good, if your probe isn't tuned to the frequencies, it can mislead you. There is a margin of error in there, and it increases as you get further out of the specifications, the range, the function ranges of the scope. So these high frequencies that travel on the surface of materials, these are still electrons. These are ionized. These are electrons separated from their host. So the host's holes had to be filled, which was taken care of on a quench cycle on the pulse. Because you have to fill the holes, or you have an imbalance. And that pulse travels out that waveguide, smacks into space, free space, with no bounds. So now that gold-plated waveguide is gone, it hits space and it travels in a general direction and goes out miles and bounces back, and somebody can see it on a computer now, CGI. It used to be one of those old two-color screens, on or off. So it was a green screen and a little motor that spun the screen around. Good old days. We have computers. Thank goodness we have computers. So there's coffee spectrum measurements and high frequency considerations. This is touching on 5G, 6G, and 27G networks. It is boundless frequencies. It is the AM radio band being redistributed and given away, and money given to religious organizations that play in those AM radio bands. That's a different story, though. Frequencies. Enjoy the glyphs.